So hello, you clicked on this video thinking you can figure out how to get a rocket to orbit in 15 minutes. To demonstrate this for you, I'll use a game also kind of like a simulator called Juno New Origins. So let's see. So here we are in Juno New Origins. I'll first set the programmed pitch of the rocket to 85 degrees so that you can make the rocket go sideways as fast as possible. This is because to get into orbit, you have to go into a continuous freefall around the Earth. Here you can see the rocket already tilting. The grey arrow on the orientation bar is the direction we're facing in, and the green arrow is the direction we're going in. On this map, we'll later be able to see the orbital or suborbital trajectory that the rocket will take. This will be very useful for planning burns later on. We'll now set the pitch to 80 degrees. This is because we have to slowly make the curve go even more sideways. So we go from 85 to 80 to 70, so on. You can see the apogee of the rocket increasing. It's around 35 kilometers right now, and we are aiming for it to get into space, which is beyond the Kármán line of 100 kilometers. We've reached the Kármán line. Time to throttle down so that we can make it towards our apogee and start throttling towards sideways. I've set this pitch to 45 degrees. Let's speed up time until we get into apogee. We only have 4% of our fuel left on this stage, but don't worry, just as most rockets do, we have more stages upcoming. You can see the trajectory that the rocket will take on the map. It's kind of hard to see right now against the blue background of the Earth, but later it will be easier to see as the trajectory will be larger. The rocket has just passed the Kármán line, which is over 100 kilometers of altitude. That means we're now officially in space. The spacecraft is almost at apogee. It's time to throttle up so that we can extend our trajectory sideways. The first stage has ran out of fuel. Time for stage separation and second stage activation. As I'm doing right now, the pitch has to be continuously adjusted to make up for the rocket's trajectory. We're approaching apogee once again. We'll throttle up and continue on our trajectory to orbit. Our time to apogee is decreasing. This is because our thrust that we're providing through the rocket is not enough to combat the speed of us coming back to Earth. Our apogee indicator has completely disappeared on our trajectory map. There's no need to worry, as we're continuously thrusting, so as our speed increases, we can once again have a point of apogee that we won't reach. The apogee indicator has returned, which means we haven't reached the maximum potential height that the rocket has. We only have 5% of our fuel left on this stage, so we'll have to stage separate and move on to the next stage. As we just stage separated, the rocket lost a lot of mass, so this final stage will accelerate significantly more than any of the other stages. You can see the trajectory stretch out as I speak. Once it stretches out enough, it will wrap around the whole Earth and turn into what we call an orbit. There is a data panel in Juno New Origins. It gives you a lot of data that you can use in the equations coming up later in this video. Keep in mind that the orbit I'm going for in this video is just for a demonstration, so it'll be very rough and won't be equal or like a perfect orbit. There might be one side that's 500 kilometers and then there might be one side that's 100 kilometers. The reason we throttle down when we're getting far from our apogee is when we're near the apogee, we use much less fuel to get a much greater distance for the trajectory stretching out. We are getting very close to reaching orbit. The trajectory is stretching out and is almost wrapped, and now it's wrapped all the way around the Earth, and there's one side that's 1,800 kilometers and one side that's 100 kilometers. Just as I said before, we aren't going for a perfect orbit. This is just a demonstration of how getting to orbit works. So as you just saw me doing a Juno New Origins, we'd got into orbit. Looks simple, right? It isn't as simple in real life, but it's not too hard. What's hard is using as little fuel as possible to get maximum payload into orbit. Let's look at some equations that go behind all of this. Keep in mind, a lot of data that you need for these equations can be found in the craft data panel on Juno New Origins, or even the individual part data panel during flight, or in the craft builder for some stuff. So let's break down the math that dictates every launch. Starting with the thrust to weight ratio equation. It is a simple equation, but its implications are massive. On the top, you have thrust, the raw propulsive force generated by the engines measured in newtons. On the bottom, you have mass times gravity, which is the actual definition of weight. If this fraction equals exactly 1.0, your thrust perfectly balances your weight. The rocket won't lift off, it will just awkwardly hover on the pad, burning fuel and fighting a losing battle against gravity. To accelerate upwards, your TWR must be greater than 1. For Earth departures, engineers usually aim for a lift-off TWR between 1.2 and 1.5. But remember, this equation is dynamic. As the rocket burns through tons of propellant every second, the mass variable rapidly drops. Because mass decreases while thrust stays constant, your TWR steadily climbs throughout the flight, forcing astronauts to throttle back down to avoid crushing G-forces before main engine cutoff. So moving from liftoff to orbit, the physics changes entirely. We're now doing the orbital velocity equation, where once you're above the atmosphere, you stop fighting gravity with raw vertical power and start using horizontal speed to stay in space. The orbital speed equation is V equals square root of gravity times the mass divided by r, which is your orbital radius. To find the exact speed, you need to stay in a stable circular orbit. You need to look at three things. The big G is the universal gravitational constant, which never changes. Big M is the mass of the body you're orbiting, like Earth, Mars, or the Moon. And R is your orbital radius, measured from the absolute center of that planet, not just its surface. Notice what's missing here? The mass of your actual spacecraft. Whether you're orbiting a tiny CubeSat or the International Space Station, the required speed is exactly the same, because everything falls at the same rate in a vacuum. The most important takeaway is that R is on the bottom of that fraction. This means altitude and speed have an inverse relationship. If you're in low Earth orbit, closer to the planet's core, gravity pulls harder, so you have to move along at a blazing 7.8 kilometers per second to keep from falling back down. But if you move way out into geostationary orbit, the radius increases, gravity weakens, and your required velocity drops significantly. Now for the ultimate reality check of spaceflight. Tsiolkovsky's rocket equation. It dictates how much change in velocity, or delta V, your spacecraft can actually achieve. It looks daunting, but it really comes down to efficiency versus weight. First, you multiply the engine's efficiency, known as specific impulse or ISP, by standard gravity. This represents your exhaust velocity. A higher specific impulse means more bang for your buck for every kilogram of fuel. The second half is where the universe gets brutal. You multiply that exhaust speed by the natural log of your starting mass divided by your dry mass. Because our natural log function is a harsh mathematical curve, adding more fuel gives you diminishing returns. To double your delta V, you don't just double your fuel, you have to increase your starting mass exponentially. It's why rockets are essentially giant fuel tanks with tiny payloads stuck on top. I hope you had as much fun as I had this video. If this video performs well, I'll make a part 2 more in depth. So please like and subscribe and share this to your fellow space enthusiasts. If you want to support my endeavors even further, donate at the link below. This is Astrox, signing off.